Hello, so in this video I'm going to talk about continuity. Now, continuity has, a simple definition and then it has the definition that you'll learn today. So, continuity means that if I can follow along a graph without any breaks or jumps, that means that the function is continuous at every single point. So here we see a graph f of x, and as you saw, I was following along the graph until I just said, okay, well, I can see that this function has no breaks. So the thing that I can say about this function is that this function f is what we can say continuous. So it's continuous on the real line. So it's going to be from negative infinity to infinity. Now notice that over here we have a different graph, g of x, and let's just notate that point over here as a. Now if I follow along here, I have that the graph, okay, yeah, it's smooth, but right here there's a hole, meaning that it's undefined. So I have to jump from here to here, because I skipped the hole, and then I keep following, and okay. So from here I observed that basically that g is discontinuous. Okay, so I'm making the note that it's discontinuous at x equals to a. But nothing's stopping me from saying, well, where was it continuous? So g is continuous on, okay, so I was able to get continuity from negative infinity to a union from a to infinity. So in this case we have kind of like a disjoint interval for the continuity. Well, normally, like whenever we talk about continuity, we actually have that there's kind of like a 3 checkpoint. So we have that if we look at the continuity pointwise for x equals to a, then basically we have that there's going to be like kind of, again, like these little checklists. So we have that f of a is defined, but then we also have that the limit as x approaches a for f of x, it must exist. Okay, so we'll just say that the limit exists. But we also have another that we can say. So we'll just say that, for example, or no, not for example, but the last checkpoint is that the limit as x approaches a for f of x, yeah, so for f of x is equal to the limit as x approaches a for, actually, sorry, yeah, it's supposed to be equal to the function value, so f of a. Okay, so if we have that any of these rules do not match up, then in that case we have that it does not exist. So let's say that we look at an example where we try to see like if a function is discontinuous. Okay, so we'll just say find if f of x is continuous at x equals to 3. And we'll define f of x in the following way. We have that f of x equals to, okay, so we have x squared minus 9 divided by x minus 3. And this is for when x cannot equal to 3. But here we'll just say that this is going to be defined as, well, 4. And then we'll just say that x equals to 3. Now, to do this problem, basically we just have to see like whether the function satisfies the three conditions. So we have that f of 3 is equal to 4. So we have that the first is actually satisfied. And then if we go to the next one, if we calculate the limit as x approaches 3 for x squared minus 9 divided by x minus 3, well, you're going to find that when you simplify this by factoring as x minus 3 and x plus 3, you'll see that the factor of x minus 3 actually cancels out. So what that does is, it reduces the limit expression. And what it does is it gives us that it's going to give us a limit. Okay, so we have a limit that's equal to, okay, so we have that the limit is equal to x plus 3. We're taking the limit of x plus 3, and that equals to 6. So, okay, well, the limit did exist, but here I check the last bit, and I find that f of 3 does not equal to the limit as x approaches 3 for f of x. Because see here, we have that it's equal to 4, and we have that it's equal to 6. So in that case, we have that f is discontinuous at x equals to 3. Now what that means is that the function is continuous, but it's basically continuous at everywhere except 3, if you want to look at it that way. So like minus infinity to 3 union 3 to infinity, and then that would be it, like in terms of the question. So one way that you can kind of look at it, like if you wanted to visualize it, is that if you graph the equation, you would find that basically it's a linear equation where it's got a point that's removed from it, and then from there you have that the point was relocated at 4. So you have that there's something like this, where you have that the point is removed from it. So we call this a removable discontinuity. Okay, so let's look at another example where we can kind of apply these different rules. So let's say that we want to find where g of x is continuous. Where it's continuous at. So here we're just going to define g of x as the following equation. We'll define it as 1 divided by x minus 2. Now here automatically we have that x is not equal to 2. So notice that basically you already have that g of 2 is undefined. But you also have that the limit does not exist. So automatically we kind of know that this means that g is discontinuous at x equals to 2. So one way that we can actually see that is by just looking at the graph of the equation, so or the rational expression or the rational function. So we have that that's going to look like 1 over x. Okay, so we have there's an asymptote right here. Now we'll talk about asymptotes. Well, actually, we did talk about asymptotes in the previous few sections. So we have that there's an asymptote right here at 2, and let's see. Okay, so I probably shouldn't have put that 2 there because I need that space. So we'll put 2 right there. Okay, so the graph of the equation looks, let me use this. So we have that it looks something like this, where we have that it decreases towards y equals to 0. Okay, so that's the horizontal asymptote. And then we have that the equation passes through here. Now, we did say that, yeah, if you take the limit from the left and the right, you get two different signs, like negative infinity plus infinity. But in either case, you have that the limit does not exist. So notice that I have that it is definitely continuous from the left and is continuous from the right, except not at 2. Now, this specific type of discontinuity is what we call an infinite discontinuity. Okay, so this tells us that we could possibly state where the function is continuous at. Technically, right away, from x not equal to 2, I automatically knew that it was not continuous at 2. And the way that I kind of think about it is like if I think of an interval line and then I have, 2, but then I have that there was like it was undefined. Well, that told me that basically everything else is included with exception of 2. So then that means that the intervals of continuity the intervals of continuity would have to be at minus infinity, comma, 2, union, 2 to infinity, and then that would be it in terms of like where it's continuous at. Now, we can actually look at more examples, and we don't necessarily need the graphs for all of them. So, for instance, let's say that we were to look at a piecewise function. So, let's say that we have a function that we just define as f of x. So, find if f of x is continuous. We'll just say that it's continuous at x equals to 0. Okay, so we want to know if it's continuous at x equals to 0. So in that case, we have that the function f of x is defined as follows. So we have that it's going to be x squared plus 1 for when x is less than or equal to 0. And then we have that it's going to be 1 minus x for when x is otherwise like greater than 0. So So for here, I need to basically go through the checklist. So we have that, okay, yeah, f of 1, not f of 1, but f of 0 is defined. And if you want to be very specific, you just evaluate what 0 is at the top. But I need to really check the limit as x approaches 0. So this means that I need to look at the left and the right. So I have f, the limit as x approaches 0 from the left for f of x. This is equal to 1, because you have that you would use x squared plus 1. Then you have that the limit as x approaches 0 from the right side for f of x, well, that's also going to be 1 because you have 1 minus x, so you plug in 0, and you have that's just going to be 1. Well, what this means is that together, this tells us that the limit as x approaches 0 for f of x, that it's just equal to 1. Now, if I look at basically the last checkpoint, well, the last checkpoint says that you need to have that the limit value is equal to the function value, but it is. So we have that f of 0 does equal 1, which is also equal to the limit as x approaches 0 for f of x. So what this means is that f is continuous at x equals to 0. Now, notice that basically that was the only possible place where you might have that it's not continuous, for instance, which basically means that, you know, if we would have had that the left limit was not equal, then yeah, we would have that it would be discontinuous, for instance. Now you can graph it, for instance, but you really don't have to because, I mean, based on the definition, we've already found that it's continuous. But like, let's say that you go ahead and you do graph it. So if you do go ahead and graph it, you'll get that the graph looks, and this is just a sketch, so we have that the graph will look like this from the left, and then it'll look something like this for the right side. Okay, so looking at this graph, I can see that basically that this graph shows that f is actually continuous. From negative infinity to infinity. So that's actually kind of interesting in the sense that, okay, yeah, it's continuous everywhere. Now let's go ahead and just look at, for instance, if we wanted to find the intervals of continuity based on a rational function. So like, let's say that we want to say that we want to find where g of x is continuous. Okay, so let's say that the function is defined as follows. So we have g of x is equal to, okay, so we have x squared plus 6x plus 8, and that's all divided by, okay, so let's see, I'm going to use like x squared plus 7x plus 10. So the main thing for this one is that basically that we realize that there's going to be two possibilities for a rational function. you have that either there's going to be an asymptote or you have that there's going to be a hole. Now, most likely you learned at some point that a rational function has to be in its most simplified form in order so that you can determine the asymptotes. But that's for asymptotes. So that means that holes would not be included, but we need those. So in that case, like we just need to look at the denominator when it's equal to 0. Otherwise, it kind of gets confusing if you factor both the numerator and the denominator, but if you at least account for the holes, then in that case, it'll be fine, I think. Okay, so what we'll do for this one, we'll just go ahead and look at what this factors to. So g of x, it factors into x plus 2 multiplied by x plus 4 divided by, okay, so this factors as x plus 2 and as x plus 5. Now note that basically we do have that a factor cancels out. So we have that that factor cancels out and it reduces our rational function as x plus 4 divided by x plus 5. But I now have that I can see that x cannot equal to negative 2. Why? Because the factor x plus 2 canceled out. But here I also see that if I set x plus 5 equal, well, let's say not equal to 0, it's really preference. Like normally in class I'll say we can set it to 0 and then just solve it and then just restrict it last, but it's all the same. So you end up with x equals to negative 5, but we don't need it to be equal to 5. So we have basically two restrictions. We have that there's one at negative 5 and another at negative 2. So what this does is it tells me that basically g is continuous at all values, all real values, all real numbers except when x is equal to negative 2 and when x is equal to negative 5. All in all, that basically tells us that you have that g is continuous on minus infinity, comma, negative 5 union negative 5 comma negative 2 union negative 2 to infinity. And then that would be where you have the intervals of continuity. Now, when we talk about continuity, usually we do talk about left-sided continuity and right-sided continuity, which, I mean, you can kind of visualize it if you were to look at, say, for example, um, like the semicircle with radius 3, for instance. So let's say that you have a circle and you have it from negative 3 to 3. Well, here I use that term left side, right side continuity because notice that here you have that if you define the function as, okay, the semicircle with radius 3, then the way that that looks is that you have the square root of 9 minus x squared. Okay, so in this case, like we're looking at like to the right of negative 3 and the left of 3. But notice that on the right of 3, it's discontinuous. At negative 3, it's also discontinuous because you have that it doesn't, it's like it's undefined from the left side and from the right side of 3, respectively. So all in all, that's just me saying that, you can have continuity on a bounded closed interval, but it's only if you have that the endpoints are included. So in that case, like, yeah, we can check all points in between negative 3 and 3. So definitely I know that it's continuous from negative 3 to 3. But then I add in that it has to be defined at -3 and 3. So what that means is that f is continuous on the closed interval from -3 to 3. So that's just like whenever we talk about continuity. On a closed interval from A to B. But you can still, throw in there like the left side continuity because, yeah, like I said, it's continuous to the left of 3 and it's continuous to the right of 3. Now, the last example that I'm going to look at is a classic problem where we have that, let's say that we want to find the value of b that makes f of x continuous. So let's say that you have a function f of x and it's defined in the following way. You have x squared minus 25 divided by x minus 5, and this is for when x cannot equal to 0, not 0, 5. But then you also have that when it's equal to 5, that you have that this is going to be a, not a, we have it's going to be bx, and then we have that that's going to be plus 2. Okay, so we have that essentially all that we need to do is just check like how to make this continuous. So first off, we have that actually f of 5 is defined. F of 5 is actually equal to 5x, not 5x, 5b. Okay, so we have 5b plus 2. Okay, so that means that we can actually then furthermore check the limit as x approaches 5 for x squared minus 25 divided by x minus 5. So we can actually factor this similarly, just like the previous problem, where we have the limit as x approaches 5, and that's going to be x plus 5, but that equals to 10. So we have that equals to 10, so we have 5b plus 2, and that's because we have to set these both equal to each other, equals to 10. But when I solve for this, like if I subtract 2 from both sides, I see that basically that gives me 5b equals to 8. But that tells me that basically that b is equal to 8 fifths. So b is equal to 8 fifths, and that makes it that makes this function continuous, meaning that this function will be continuous everywhere once you set the b to 8 fifths. Now, there are some problems of which that, you'll have that, how do I say this? That it's possible that well, that it's not possible that you can't make the function continuous. Because, for instance, let's just think, for example, that you don't have necessarily a constant that you're looking for, but like if you have something like that g of x is defined in the following way, such as like you have x squared plus 1, and then you have that that's going to be for when x is greater than or equal to 0. But then let's say that you have that this is going to be such that you have like x plus 2 for when x is less than 0. Well, for this one, first off, you have that, okay, yeah, g is defined. And I mean, if you want to put a b, for example, uh, like if you put it, well, it's already too late to introduce a b, but yeah, anyways, but we can just ignore that, the whole thing about finding constants, because like notice that, yeah, g of 0, it is defined, but then when you look at the limit of g of x, okay, so the limit of g of x as x approaches 0 for g of x, you'll find that the limit doesn't exist. So this means that the function is discontinuous at x equals to 0. Now, to kind of like visualize it, like why is it not possible that the function is continuous at 0? Because like, I mean, we were able to redefine the previous problem so that it's continuous, but for something like this, you have that it's just not possible unless like you have that you just redefine the rules. So like x squared plus 1, let's see, x squared plus 1, that looks something like this, where you have a parabola. But then, actually, that's on the wrong side. Yeah, so you have the parabola goes like that. But then x plus 2. Okay, so x plus 2, you have that that's actually going to be like this, where you have a hole right there, and then you have that it just goes like this. Well, here there's basically kind of like a jump. So here you have that that's a jump discontinuity going from 0 to 2. So in that case, like I would say that like it's just not possible that we can get this function to be continuous unless like we were to redefine the rules and say that, okay, yeah, maybe like if this 2 was rewritten as a 1, then yeah, we would be fine, but it's not. So in that case, it's just impossible to redefine it. Yeah, unless we throw away that function and then throw in x plus 1 or something like that. Okay, so with continuity, you just have to go through the process of checking the checklist. With intervals of continuity, you just have to look at where it's defined in that sense.